Alright, welcome to page 3, and what we're going to do on page 3 is just talk about the curvature of basically our curve. And so a parametrization R of t, so of our vector, is called smooth on an interval at I if r prime is continuous and r prime of t does not equal 0 on I. So it's basically, where our function can be differentiable. So it's not at any cups or there isn't any jumps in our curve. And so a curve is called smooth if it has a smooth parametrization. A smooth curve has no sharp corners or cusps. When the tangent vector turns, it does so continuously. So if C is a smooth curve defined by the vector function r, recall that the unit tangent vector t indicates the direction of the curve and is given by so here's just our vector, our unit tangent vector, and this is just recalling what we learned in previous chapters. The curvature of C at a given point is a measure of how quickly the curve changes direction at that point. So the curvature of a curve is simply the Greek letter kappa is equal to, it's basically how our tangent vector is changing with respect to our arc length. So that's why it's d of bold cap t over ds, where t is the unit tangent vector. All right, and so basically what the curvature is how curvy is our curve. If we had a curve, say, that looks something like this. All right, I wanted to draw this just a little bit straighter. So there we go. All right. Here, our tangent vector, when we're going right here, it's not very curvy at all. So our tangent vector is not really changing a whole lot. Then once we get here, it changes some, but then it becomes, more like a line. So when we're talking about curvatures, like how less of a line does your, curve make? And then when we get here, our vector, our tangent, should be changing quite a bit. And so our tangent vector is going to help us determine how curvy our curve is. And, we're always going to take this with respect to our arc length, how far we're going on the line. Helps us tell, our curve. And so that's why kappa is the way that it is. So the curvature is easy to compute if it is expressed in terms of the parameter t instead of s. So instead of saying ds, we can write kappa of t is equal to the derivative of the unit tangent, the magnitude of the derivative of the unit tangent vector equation over the magnitude of r prime of t. And why that is because we're taking these, we want to know as time goes along where we're taking these. So if kappa is equal to d of t over ds, and we're taking both these with respect to time, then what we can say is d of t d cap t over d of t over ds over d of t with respect to both time is going to give us kappa and then unit tangent, because we're taking the derivative of cap t of t and then ds over dt. If you recall from last page, that's just going to be r prime of t and the magnitude of that. All right, so let's find the curvature of something that we have. And so in this case, it says show that the curvature of a circle of radius a is 1 over a. And so the first thing what we want to write is we want to write our r of t. And so what we can do is we can take the circle to have the center, the origin. So our center is going to be the origin. And then a parametrization is, so we can write r of t is equal to a cosine t I plus a sine t j. Instead of writing, x minus, 0, y minus 0, putting these in terms of time, so a cosine ti plus a sine t j. And now what we want to do is we want to go ahead and take the derivative. So r prime of t is going to give us negative a sine ti plus a cosine t j. So our the magnitude of r prime of t is going to equal the square root of negative a sine t squared plus a cosine squared t, which is just going to give us the square root of I'll write it out. A squared sine squared t plus a squared cosine squared t. We could pull out an a squared sine squared t plus cosine squared t. So it's going to give us the square root of a squared, which is just a. Alright, now if we do our tangent, so if we do t of t, that's just going to be r prime of t over the magnitude of r prime of t. And that's going to give us negative a sine t, a cosine t, all over, when we just found this a, so we're just going to have negative sine t cosine t for our vector. And then if we wanted to take the derivative of that, we're just going to get negative cosine t, negative sine t. And now we want to find curvature. And so our curvature is going to be k of t is equal to derivative of the magnitude of the derivative of tangent t over the magnitude of the derivative of r of t. And we found this to be negative cosine square root of negative cosine t squared plus negative sine t squared all over a. That's going to give us the square root of cosine squared t plus sine squared t all over a, which is just 1 over a. And there you see that the curvature of a circle with a radius of a is going to just be 1 over a. Now, the formula given by the following theorem is the one that's going to be more convenient to apply, because we don't really have to find the tangent vector and we can just use the vector that's given. So the curvature of the curve given by the vector function r is kappa of t is equal to the magnitude of the cross product of the derivative times the second derivative over the magnitude